Welcome to the second session on Combinatorics. As usual here, we shall have two lectures in the first part and then a break of 30 minutes followed by another lecture. We have got a terrific lineup of speakers. We should be in for a treat. Our first lecturer is a brilliant young Korean-American mathematician, Jun Ha. He is a Clay Fellow at the IAS, the Institute for Advanced Study in Princeton, and also at Princeton University. He's working on applications of algebraic geometry to combinatorics and has proved a number of great results. Although he got his PhD only in 2014, he has already published 14 great papers, and another substantial paper on applications of Hodge theory to combinatorial geometries is about to appear in the Annals of Mathematics. Ladies and gentlemen, please welcome Jun Ha to deliver his lecture.
It is a great pleasure and an honor to be able to speak here. Thank you for the invitation and thank you for coming. So today I will talk about combinatorial applications of the Hodge-Riemann relations. But let me say in the beginning that my goal today is not to communicate the details of some specific statements, some specific mathematical statements. But rather, my goal today is to convince you that there is a worthwhile mathematical theme to keep in mind and think about it from time to time. So please sit back and relax and don't pay any attention to many of the details that I'm about to show you on the slide. Okay, so combinatorial applications of the Hodge-Riemann relations. So eventually, I will going to tell you what I mean by Hodge-Riemann relations, but I will start by something way more simpler. These are two notions that applies to a sequence of real numbers. The first is that of log-concavity, which says that if you have a sequence of real numbers ai, then the displayed quadratic inequality holds for every index I. ai squared is at least as large as ai minus 1, ai plus 1. And it's known that, and it's easy to see, that if all the entries ai are positive, then log-concavity implies the unimodality, the condition which says that there's a single peak in the sequence ai, and hence the name unimodality. So, as they are, these two notions are way too simple to be mathematically interesting. But the one reason why they are interesting is that many sequences that naturally appear in various parts of mathematics turn out to be log-concave and or unimodal. Some of the early collection of such occurrence of log-concave and unimodal sequences in mathematics are collected in the classic surveys by Stanley and Branty in 80s and 90s. And I'm sure if somebody decides to compile an update, there will be plenty of new additions to these sequences that arise in algebra, combinatorics, and geometry. So why do natural and interesting sequences so often turn out to be log-concave? There can be many different explanations, but today I will propose one of those many possible explanations from the viewpoint of what I would call standard conjectures. From this point of view, what makes the occurrence of unimodal and log-concave sequences interesting is not only because of their ubiquity, but of their implication that there is an object which explains unimodality or log-concavity in the strong form of standard conjectures. So let me start afresh by saying that X is some mathematical object with a sufficiently rich structure. That's a terribly vague statement, but let me compensate that by showing you a few examples of objects that definitely count as having sufficiently rich structure. So my first example would be the case when X is a compact Kähler manifold, say something like a Combinatorial C to the D modulo a full rank lattice lambda. Or maybe my X is a convex polytope, say of dimension D, say a cube or dodecahedron or any other interesting polytope that you can imagine. Or my X may be a projective variety, something like a Riemann surface or higher dimensional versions of it, defined by homogeneous equations. Or my X may be a Coxer group, say an infinite discrete group generated by reflections that represents the symmetry of, say, the first picture, tessellations by triangles. Or my X may be what is known as a tropical variety of dimension D. This is a piecewise linear object, which is often but not always is obtained by tropicalizing algebraic or analytic objects, and they look like that. And I will focus on the particular case of linear tropical varieties, which bijectively correspond to the classical combinatorial object called matroids. I'll get back to this case. So I have shown you some random sequence of mathematical objects, 5 of them. And you may wonder, what do such objects have in common? So on the surface of it, they look very distant from each other. But the point that I want to emphasize is that they all individually satisfy what I would call standard conjectures. I'll get back to more detailed statements, but roughly speaking, by standard conjectures, I'm referring to the collection of 3 statements that I'm going to label by PD, HL, and HL. So PD, we're going to be the statement of the form which says that X satisfies the Poincare duality. So this statement will, of course, very much depend on what X you have in mind and what you actually mean by Poincare duality. But in any case, you will have a certain natural sequence of vector spaces or a graded vector space attached in some natural way to your object X. And Poincare duality will state that if you look at the case member of your sequence of vector spaces and D minus case member of your sequence of vector spaces, there is some natural non-degenerate pairing between them, so that the dual of the first vector space is naturally isomorphic to the second vector space. The second entry, HL, will say that your object X satisfies Hart-Lefschetz theorem, and it also refers to this graded vector space naturally attached to your object X in some way. Unlike Poincare duality, the Hart-Lefschetz theorem will tell you that the case vector space is isomorphic in some explicit way to D minus case vector space, not the dual of D minus case vector space. And furthermore, this isomorphism will factor through all the intermediate vector spaces that lives in between the case and D minus case entry. And the last entry is the Hodge-Riemann relation, which is the topic of my talk. and it's the least known of the three to general mathematical audience. PD and HL are somehow complementary to each other in the sense that one says that one vector space is dual to the other vector space, and the second says that the same vector space is isomorphic to the second vector space. So you can compose these two isomorphisms to get a bilinear pairing on one of the two vector spaces. And if you're using real numbers as coefficients for these vector spaces, you will usually get a symmetric bilinear form, and hence you can talk about the signature of the bilinear pairing obtained in this way. And the Hodge-Riemann relation tells you exactly how many positive eigenvalues and how many negative eigenvalues you must see on this pairing in terms of the graded dimensions of the vector space associated to X. In most known cases, formulating these conjectures precisely for your given object X and proving standard conjectures for X are both difficult. I'm even inclined to say that in all known cases, both formulating and proving standard conjectures are difficult. But when we can do it, it was always worthwhile. So let me start with the Hart-Lefschetz theorem, which is more classical and better known in combinatorics community. So Richard Stanley in the 1983 ICM summarized the known applications of the Hart-Lefschetz theorem to combinatorics in that article. And in his talk, he emphasized two applications. The first is Air-Moser Conjecture, which is a statement about a subset of real line. So if you have, say, a finite set of real numbers, you write Fe of a k for the number of subsets of E whose elements sum to k. And the conjecture predicts that this number Fek is maximized in the case when E is evenly distributed set of integers in between -n to n, centered at 0. So it's not so easy to see a connection between this statement with a version of Hart-Lefschetz theorem, which said that some vector space is isomorphic to some other vector space in a certain way. But there is a certain poset that you can construct in this setting, and the inequality that you're seeing in the display is in fact a version of Sperner theorem, which gives an extremal value of the size of the antichain in these posets. And there's a famous way of proving that certain posets satisfy these Sperner properties, which is to show that certain sparse matrices have full rank, and therefore producing a matching between certain rank level sets between the poset. And that is a version of the Hart-Lefschetz theorem that Stanley used to deduce this result in extremal combinatorics. The second one, perhaps better known application, is to McMullen's G conjecture. The G conjecture provides a complete numerical characterization of the so-called H vector of a simplicial polytope. And the H vector is a sequence of real numbers hi that contains exactly the same information as the sequence of integers fi, which counts the number of i-1 dimensional faces of your polytope P. And fi and hi are related by linear transformation, which recovers each other by the polynomial identity displayed over there. So among other things, the G conjecture gives a necessary condition for a sequence to be a H vector of a simplicial polytope, and two of the most famous consequences of it is that hi should be equal to hd minus I, which is the numerical shadow of Poincare duality, which is what's known since antiquity and known as then-Somerville relation on simplicial polytopes. And a numerical shadow of Hart-Lepcher theorem, which says that hi is bounded above by hi plus 1 for every I less than d half. Let me add one more recent application of the Hart-Lepcher theorem in elementary combinatorics. Perhaps this is even more elementary to state than the previous two conjectures, as it concerns linear algebra and nothing more. So let's consider the following statement. Pick a finite set of vectors and call it E, and write Wi for the number of I-dimensional subspaces spanned by subsets of E. There will be certain number of them, very much sensitive to the position of vectors that you have chosen. And the statement is that if E spans a d-dimensional space, then Wi, the number of I-dimensional subspaces, should be at most the number of codimension I spaces, and also the number of I-dimensional spaces will be bounded above by number of I plus 1-dimensional spaces spanned by subsets of E for every index I, which is at most d half. And there is also a certain Hart-Lepcher theorem which explains these numerical and combinatorial inequalities. And as you can see, the statement itself refers nothing more than the linear algebra. Just linear independence of vectors and nothing more. But unlike the previous two items, 1 and 2, no elementary proof of this statement is known. So the current proof uses the Hart-Lepcher theorem for L-adic perverse sheaves based on the fundamental work of Beilinson, Bernstein, Delin, and Gaber. And without that general machinery, currently there is no known justification of the two inequalities. But the situation was just like this for the items number 1 and number 2 when these applications of the Hart-Lepcher theorem was first discovered. Once this result was found, people noticed that the Hart-Lepcher theorem that's used in this particular context can be formulated and even proved just using elementary combinatorics, or the language that's inherent to the object X in question. So presumably the same thing will happen to this statement also in near future. So let me start talking about combinatorial applications of the Hodge-Riemann relations that cannot be obtained by, say, Hart-Lepcher alone. So it's a little bit more tricky to state the Hodge-Riemann relation, but there is a very pleasant quote, maybe the earliest reference, at least the one I could find, that emphasized the importance of the Hodge-Riemann relations. So this is a letter from Serre to Grothendieck in '64, which starts like this. There's a young Italian Bombieri who is working on zeta functions, and he noticed all by himself that it was necessary to prove in all characteristics that the intersection form on primitive algebraic cycles of half dimension is definite. So that sentence is the statement of the Hodge-Riemann relations. And as you can see, apparently it's supposed to play some role in the theory of zeta functions on projective varieties over finite fields. So let me try to make the statements a little bit more formal, but not entirely rigid yet. So let's suppose for simplicity that X is sufficiently smooth. whatever that means. And that will, of course, depend on the context, what your x is. And under that simplifying assumption, the three statements, PD, HL, and HL, will roughly look like this. First of all, one looks for a triple of mathematical objects that's somehow naturally attached to your x. And the first one among the triple is a graded commutative algebra over the real numbers that I'm going to write by AX. And this is a vector space, a graded vector space, where the grading goes from 0 to D, where D is the dimension of your object X. For convenience, I'll refer to this as the cohomology ring of X. The second character that you are looking for is a linear bijection from the top graded component, A to the D, to the real numbers all. I'll call this linear isomorphism the degree map of X. You should think of this as an analog of the orientation. And the third character that you're looking for is a non-empty open convex cone which lives inside the first graded component. I'm going to call this cone the Kähler cone of X and write by the letter Kx. It is a some full-dimensional convex cone that lives inside, say, the finite-dimensional real vector space A1. So these are the three main characters that you need to state the standard conjectures for your X. So usually, one of the most non-trivial part of this game is that given X, come up with a natural and interesting triple of algebra, isomorphism, and a cone that may have interesting properties. So when you have found these triple of objects, then you can formulate a triple of conjecture in this way. Let's say you have a sequence L0, L1, L2, all picked from this Kähler cone Kx. And you pick an index Q, which is at most D half. The Poincare duality will state that the multiplication in your ring AX defines a non-degenerate bilinear form, a pairing between the degree Q part and degree D minus Q part, which is essentially obtained by multiplying two things together and apply the degree map to make it into a real number. And the second part, the Hodge-Lefschetz theorem, will state that the multiplication in AX defines an isomorphism between the degree Q part and degree D minus Q part, which is obtained by multiplying a given element H of degree Q by the sequence L1, L2, dot, 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 L to the D minus 2Q, all of degree 1. And the third part, the Hodge-Riemann relation, will tell you how Poincare duality and Hodge-Lefschetz interact with each other. So if you look at the symmetric bilinear form defined on the Qth degree part, AQ, obtained by sending H1 and H2 to their product and the L1, L2, dot, 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 L to the D minus 2Q, and apply the degree map to turn it into a real number, decorated with the sign minus 1 to the Q, then the statement is that such a bilinear form is positive definite, not on the whole space, but on the kernel of the multiplication by Li, where this time you are multiplying by one more Li, namely L0, then that would give an isomorphism in the Hodge-Lefschetz theorem. So there will be a non-trivial kernel in general, and Hodge-Riemann relation tell you that the restriction of the bilinear pairing is positive definite on that kernel. So these are the three statements. And admittedly, this is not entirely familiar to many of us. But this is exactly the reason that I want to advertise these properties to combinatorial audience. These properties appears to be, so far, both ubiquitous and fundamental. And for some reason, they're usually difficult to formulate and prove. But I think this is the artifact of the way how we are mathematically trained. If we do look for them actively, then maybe we will be able to find many more objects not listed on the, not among the list that I've shown you in the previous slide, that do satisfy these three properties and have wonderful implications. So here is a very incomplete list of people who contributed to this story. So classical results was famously obtained by Lipschitz, who proved his hard theorem, which nobody could understand. So Hodge proved it using his theory, and 3 years later he gave more correct proof, and 3 more years later he gave even more correct proof, and 2 years later Hermann Weyl gave a correct proof. And there were foundational results in the 80s concerning perverse sheaves and intersection cohomology and mixed Hodge modules and like that, extending the previous results to the case when things are not sufficiently smooth. And in the specific context of convex polytopes and Coxeter groups and special class of tropical varieties, various people were involved in this story. And except with the notable exception of projective varieties and Algebraic cycles in it, the three statements PD, HL, and HL are successfully formulated and proved. So at this point, you may choose to believe or not believe that these PD, HL, and HR are really ubiquitous. Certainly, there are no logical implications between Poincare duality, Hart-Lipschitz, and Hodge-Riemann relation across these various different kinds of mathematical objects, although there are non-trivial overlaps between them. But I think it's clear that for some reason they are really fundamental, in the sense that whenever you are able to formulate and prove such statements, it implies something much more concrete, certainly less abstract, and that is very appealing. And at the same time, when you could prove some fundamental statement like G conjecture, which follows from the Hart-Lipschitz theorem for convex polytopes, it is very hard to prove the same statement, say G conjecture, without first proving the Hart-Lipschitz theorem. So in that sense, standard conjectures appears to be fundamental. I want to mention that before all this happened, there was an observation by Tessier and Kovansky in the late 70s who noticed the implication that the Hodge-Riemann relation for toric varieties, in the very special case when you're looking only at degrees 0 and 1, implies something very classical in convex analysis, namely the Alexander-Fenchel inequality for convex bodies. I think this episode was instructive to many of us, including myself, because it tells you that behind these very concrete statements like Alexander-Fenchel inequality, which controls the volumes of convex bodies, there is this abstract structure, in fact, this triple of ring, the degree map, and the cone of positive elements, which explains these numerical inequalities. And the same can be said for the G conjecture and Weil conjecture and the Cousin-Lucy conjectures. There are some very elementary numerical consequences of these conjectures, which can be naturally illustrated by these more abstract structures. So I propose to look for more such structures for new class of objects X. And I think it's quite unlikely to straightforwardly come up with the correct notion of triple and prove these three statements. We have to have some sort of algorithm for guessing the correct triple. And usually the first hint for this comes from the very special case of the Hodge-Riemann relation. In fact, the Hodge-Riemann relation for degree 0 and 1, just like the case of Tessier and Plansky. It's easy to see that if you have a Hodge-Riemann relation, say in degree 0 and 1, then for any sequence of elements L1 and L2 all picked from this scalar cone Kx, any matrix representing the bilinear form on the first graded piece A1 obtained by multiplying two degree 1 elements H1 and H2 with this product of Li's should have exactly one positive eigenvalue. So if you accidentally stumble upon a certain natural matrix that for some reason have exactly one positive eigenvalue, I think it's a good sign of the existence of the more general Hodge-Riemann relation behind the whatever object that you are studying at that point. And this connects to the log-concavity of sequences, because the log-concavity of a sequence, say a triple A and B and C, can be interpreted as a very, very special case of this phenomenon. Namely, ABC is log-concave exactly when the symmetric matrix, 2 by 2 symmetric matrix ABBC, has non-positive determinant, which can be explained by the fact that such a matrix has exactly one positive eigenvalue. So, in fact, I'll show you some examples when we actually did accidentally stumble upon Hodge-Riemann relations in this context. So maybe the earliest example is that of mixed discriminant. So this is a real number attached to a sequence of D real symmetric D by D matrices. That's obtained by partially differentiating certain polynomial, the determinant polynomial, which controls the interaction between linear combination of matrices and the act of taking determinant. In the 30s, in the process of proving his Alexandrov-Fenchel inequality on mixed volumes, Alexandrov came up with a lemma which says that for any positive semi-definite matrices, say A3 dot 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 AB, the bilinear form that pairs two real symmetric D by D matrices and outputs mixed discriminant of the two matrices together with D minus 2 positive semi-definite matrices always have at most one positive eigenvalue. And this can be interpreted in the previous sense as a very special case of the Hodge-Riemann relation. And in the very important special case, when all the matrices are diagonal, the mixed discriminant is a permanent, the determinant without signs. And if you apply the previous theorem to this very special case, you have the log-concavity inequality for permanents. Say when you have non-negative column vectors AI, which you may also view as diagonal matrices of the same size, then there is a quadratic inequality between permanents of A1, A2 and A1, A1 and A2, A2. And this inequality is what's behind Gorbaczev's and Felixman's proof in the 80s of van der Waerden's conjecture that the permanent of any doubly stochastic d by d matrix is at least d pectoral divided by d to the d. So this van der Waerden's conjecture may be interpreted as the first significant applications of the Hodge-Riemann relation in combinatorics. There are so many other matrices that accidentally have exactly one positive eigenvalue. And here is another example that you may stumble upon by accident. So let's say you have a n spanning set of vectors, Vi, and you define this matrix, symmetric n by n matrix Bm, by saying that all the diagonal entries are 0 and non-diagonal entries are the number of bases containing Vi and Vj. So it's a basis counting matrix for a vector configuration. And it's not too hard to show that this matrix Bm has at most one positive eigenvalue, no matter what your vector configuration is. And in fact, if you know matroids, the same statement is valid for arbitrary matroid and can be proved in a completely combinatorial manner. But such concrete statements suggest that we should look for more delicate algebraic structures which has the full capability of expressing Hart-Lefschetz and the Hodge-Riemann relation, not just in degree 0 and 1, but in every degree. So in the remaining part of my talk, let me try to show you one very concrete case with full statements how Poincare duality, Hart-Lefschetz, and Hodge-Riemann relation may look in practice. It is non-trivial, but maybe not as difficult as we may imagine. And I think the same will be true for many of the objects that's waiting to be discovered. So maybe the first step is to look for log-concave sequences. And when you have found them, you try to upgrade such a result or observation to the existence of certain matrix with exactly one positive eigenvalue. If you succeed, this is step 2, and then you're ready to look for this algebra, A, and the positive concave. So let's consider, for example, the chromatic polynomial of a finite graph. It's a function that counts the number of proper colorings of vertices of the graph using Q colors. So for example, if you have a graph with 4 vertices, you'll have a degree 4 polynomial, which will turn out to have integer coefficients with alternating signs. And you can, in principle, compute the chromatic polynomial of any graph using the obvious recursion that deletes an edge from a graph and contracts an edge from a graph. Or you can think of a similar invariant, this time for a finite configuration of vectors. So if you start with a vector configuration A, then you can count linearly independent subsets of A, which has cardinality I, and call it Fi of A. So if you have these 7 vectors in 3-dimensional vector space over field with 2 elements, then the sequence is 1, 7, 21, 28, 7 for the 7 points, 21 for the 7 choose 2, 28 for the 7 choose 3 minus 7. Again, you can compute this Fi basically using the same recursion, which says that Fi of A is that Fi of A delete 1 vector plus Fi minus 1 of A project from that same vector. What is non-trivial from this defining recursion for chromatic polynomial and the Fi is that these numbers, the coefficients of the chromatic polynomial and the sequence Fi, individually satisfy log-concavity inequalities. And as you can expect, these statements turn out to be special cases of the Hodge-Riemann relation, which you can upgrade to the full-blown algebraic statement. And the relevant object X here is the previous mentioned matroid, which form a special class of tropical varieties. So let me show you one possible definition among many of a matroid. That this interesting theory of matroids exists was witnessed more or less simultaneously by many people in the 30s. And one way to formulate their axioms is to say that a matroid is a collection of subsets of a finite set E, which satisfies one empty set is in the collection, say a flat, and the entire set E is also in the collection, a flat. And the second axiom says that the intersection of two flats is a flat. And the third axiom says that if F is a flat, then those flats that are minimal among flats properly containing F partitions the elements not in the given flat F. And these axioms 1 to 3 are clearly motivated by the properties of the projective geometry, finite projective geometry. And it has interesting interaction with algebraic geometry. Because not every matroid, in the sense of previous 3 axioms, can be realized as a point configuration of a projective space defined over a field. For example, the first matroid can be represented over some field K if and only if the characteristic of that field is 2. And the second matroid is representable over K if and only if the characteristic is not equal to 2. And it was recently shown by Peter Nelson that almost all matroids are not realizable over any field. So although there are some interesting overlap between algebraic geometry, largely the theory of matroids cannot be covered by the theory of algebraic geometry, which is governed by the theory of fields. So you can define this characteristic polynomial for arbitrary matroid M by the similar recursion that we have seen for the chromatic polynomial, deletion and contraction. And in fact, the same log-concavity result hold for arbitrary matroid and their characteristic polynomials. And this implies the previously introduced log-concavity conjectures on graphs and vector configurations. So when M is realizable over a field, this conjecture can be proved using results from algebraic geometry, but not in the general case. So I'll very quickly show you how the actual triple that obeys the standard conjectures looks like in this particular case of matroids. So this is a part where you should not focus too much attention on details. I'm only trying to convince you that this can be done. So you need to define triple of objects, and the first among them is a ring. And the ring in question turns out to be a polynomial ring modulo 2 types of relations that are governed by the combinatorics of the matroid. And of course, there are works of many, many people, notably De Concini, Procesi, and Feitner-Izvinsky, that allowed us to arrive at such definition. But once this is done, then it's not so hard to come up with the other characters that plays the role in the statement of the 3 properties. So the second character, which is the degree map, the isomorphism to the top degree component to the real line, is again given to you by some very explicit combinatorial requirement. And lastly, the Kähler cone, or the ample cone, can be again described explicitly by the notion of strictly submodular function on the Boolean lattice on E, the ground set of your matrix. So you have your three characters, and now the three statement makes perfect sense. For any matroid, this ring that was briefly shown to you before do satisfy Poincare duality, do satisfy the Hodge-Lefschetz theorem, and do satisfy the Hodge-Riemann relations. And these three properties explains many of the elementary consequences of theirs that can be checked by playing with examples. So let me finish my talk by recalling you what just happened. So a convex polytope may be rational or not. When they are rational, the standard conjectures that they do satisfy can be explained using algebraic geometry. And this is, in fact, where people come up with the formulation of the three properties for the general convex polytopes. A Coxer group or a Coxer group element, this may belong to a Weil group or maybe not. When it is coming from a Weil group, then the Poincare duality, Hodge-Lefschetz theorem, and the Hodge-Riemann relation can be explained using the corresponding results in algebraic geometry, but not in the general case. For a matroid, it may be representable over a field, or maybe not. When it is representable over a field, the three properties can be explained by the corresponding three properties from algebraic geometry, but not in the general case. So you may wonder at this point whether this connection to algebraic geometry is truly an essential one. Certainly it is true that the first kind of mathematicians who noticed these three properties were algebraic geometers or some kind of geometers. But this may be an accident triggered by some subtle initial conditions in history. So in an alternative universe, I can imagine where these three properties are discovered by some other types of mathematicians, and the link between various objects that do satisfy the three properties for individual reasons may be found via different routes. And as you can see, these statements are not too familiar to most of us. So unless you are actively seeking for these three properties, it's highly unlikely that we will just accidentally find one of these statements. But I think, to be optimistic, we are now mature enough to look for some other new objects that is completely independent from algebraic geometric settings that do satisfy Poincare duality, Hodge-Lefschetz theorem, and the Hodge-Riemann relations. My hope is that this happens in not too distant future. I'll stop here. Thank you.
Thank you very much, June, for the wonderful talk. Are there any questions? Yes.
Is your proof of, say, log-concavity of the coefficient of chromatic polynomial somehow based on the induction of the definition of this chromatic polynomial?
It is true that it's some sort of induction, but not the obvious deletion, contraction, recursion that I have shown you. Right. Somehow, even knowing all the proof, it's extremely technical and seems unnatural to bypass the Hodge-Riemann relation. You have to first prove the Hodge-Riemann relation by completely separate reasoning, and from that you have to deduce the log-concavity.
Yes, we had another question there.
Hello. Thank you very much for your talk, very, very nice talk. And so you have this kind of general picture of which kind of ingredients give you the standard conjectures. Do you have also like a kind of wide pictures of which kind of ingredients you need in your combinatorial problem or the combinatorial side to maybe build a bridge with the standard conjectures? Because, for example, I see that log-concavity you show that can be reformulated as this problem on eigenvalues of the matrix. But do you have like other ideas or other examples of combinatorial problems like that?
So I don't have a very good understanding. So if you look at the various proofs of this Hart-Lefschetz and Hodge-Riemann for different class of objects, then they look pretty similar on most places. But there is always one place where miracle happens for completely separate reasons for each one of the individual objects. And no, they look completely different, but they all hold for different reasons. Maybe that's how the nature is. I don't know.
We have one more question in the back.
So just I wanted to ask that you find a mixed determinant. So I wanted to ask, does it have some geometrical meaning? Means like in one determinant we have to give some volume, some sense. Like we have 3x3 matrix that gives volume of certain. And so does it have similar type of geometrical meaning?
So yeah, geometry in some sense, you can interpret them as volumes of certain very special kind of convex bodies. Or you can interpret them as some intersection numbers on some projective variety. But yeah.
Maybe one more, and then I come back to the front.
Poincare duality and Hart-Lefschetz property holds in a more general context in an algebraic sense. Do you know a way of generalizing Hodge relations in this context over an arbitrary field?
I'm not sure I understand the question, but I'm pretty sure that the answer is I don't know.
Okay, and here is one more question.
Yes, thank you very much for the interesting talk. And in the representation theory, there is a case such that there is no geometrical interpretation, and then the good property fails. And there is such an instance in your framework?
You mean in the case of Coxeter groups?
Or I don't know which case, but...
So I do not know any instance of a case where these three properties can be naturally formulated and appears to be true, but in fact not true. So if somebody has a good example of this, I would love to know. Yeah.
Okay, let's have just one more question, last question.
Okay, so thanks for the talk. So as far as I understood, so you are going to restrict the result on the characteristic 0. So is this because in the cases that the algebraic geometry come into account, so use the resolution of singularities or for other reasons?
I did not restrict in any case to characteristic 0.
Okay, so don't you use the resolution of singularity?
No, nothing.
Never.
Yeah.
Thank you.
Okay. Thank you very much indeed. So let us thank Jun Ha again for his excellent talk.